In this class, let us consider wave speeds in different media. Let us recall that waves can be classified into transverse waves and longitudinal waves. Okay, the two types are transverse waves and longitudinal waves. This classification is based on the idea that if the um, suppose you consider waves traveling through a medium. So we know that when an energy or disturbance passes through a medium, the particles of the medium will be vibrating about their mean position. If the direction of propagation is perpendicular to the vibrations of particles of the medium, okay, if the direction of propagation of the wave is perpendicular to the vibrations of particles. So for example, particles of the medium vibrate in the y direction and the wave is propagating along the x direction, then such a wave is called transverse wave. If the direction of propagation of the wave is perpendicular to the vibrations of the particles of the medium, such a wave is called a transverse wave. For example, waves on a water surface. Okay, it is a transverse wave. Waves on a stretched string is a transverse wave. And if in the same sense, the other kind, if the vibrations of the medium, if the vibrations of the particles of the medium are along the direction of propagation, or if the wave is propagating parallel to the direction of vibration of the particles of the medium, it's called a longitudinal wave. Most important example is sound wave. Okay, sound wave passes through air in compressions and rarefications. So here the air molecules will be vibrating parallel to the direction of propagation of sound. So that is longitudinal waves. And longitudinal waves can pass through not only through air, it can pass through solids, liquids, etc. So when these longitudinal waves are also called since these longitudinal waves propagate by compressions and rarefactions, they are also called compressional waves. Another word for longitudinal waves is compressional waves. Also they are called elastic waves. Elastic waves. Okay. So these compressional waves or elastic waves can pass through liquids, solids. Okay, that's also possible. The waves formed by the earthquake. Okay, that is passing through the surface of the earth. It's a longitudinal wave. Okay. Okay. I think the transverse waves are also there. In an earthquake, both types of waves are possible. Yeah. And regarding transverse wave, one more point is that we have used the classification based on waves traveling through a medium. But consider waves that do not require a medium. For example, electromagnetic waves. Electromagnetic waves through vacuum, there is no medium here. They are transverse waves. How do we say that? Because in electromagnetic wave, you might have studied that there are electric field and magnetic field. Electromagnetic wave is a combination of electric field and magnetic field. So the vibrations are happening for electric field and magnetic field. Oscillation takes place in electric field and magnetic field. These variation in electric field and magnetic field are mutually perpendicular, and the direction of propagation of the wave is perpendicular to both electric field and magnetic field. For example, we can visualize electromagnetic wave as let us say electric field is vibrating along x direction and magnetic field is vibrating along y direction. The wave will be propagating along z direction. Okay, so the propagation of the wave is perpendicular to the vibrations of both electric field and magnetic field. So in that sense, electromagnetic wave is also a transverse wave. That means these vibrations need not be vibrations of particles of the medium, as in the case of material waves. Waves in material media, it can be vibrations of electric and magnetic fields. Okay, so if the direction of propagation of the wave is perpendicular to the vibrations of either the particles of the medium or the vibrations constituting the wave, then it's a transverse wave. We have seen the examples. waves on water surface, waves on stretched string, and electromagnetic waves. These are all transverse waves. Then if the direction of propagation is parallel to the vibrations of the particles of the medium, then they are longitudinal waves. Okay. Um, they are also called compressional waves and elastic waves. Let us see the wave speeds in different media. We don't derive these results, we just look at the different possible expressions of wave speeds. So first, transverse waves. Consider transverse waves on a stretched string. The expression for the wave speed is square root of t by mu, where T is the tension or force on the string. T is the tension or force on the string, and mu is it's called mass per unit length of the string. Mass per unit length measured in kilogram per meter. It's also called linear density, mass per unit length. This is the transverse wave, velocity of transverse wave. The expression for the speed of transverse waves on a stretched string. Now consider longitudinal waves. Okay. Longitudinal waves, as I have expressed before, longitudinal waves are also called compressional waves. They are also called elastic waves. We can also call them sound waves. Okay. The only point is that even though we call them sound waves, they may not be, only a small frequency range is audible to human ear, 20 hertz to 20 kilohertz. Okay, so there can be sound waves lower than 20 hertz and higher than 20 kilohertz, having frequency infrasonic and ultrasonic. Okay, so generally let us call them sound waves, or this longitudinal waves or elastic waves, or sound waves, or sound waves. They need not be audible always, that's all. So let us consider three cases. Sound waves in a solid. Sound waves in a solid. Now for this, the wave speed can be expressed as square root of y by rho, where y is Young's modulus of the material of the solid, and typically Young's modulus is of the order of 10 raised to 10 kilogram Newton per meter square, right? Newton per meter square. Yeah. And then rho is density of the solid, density of the material of the solid. Density is typically of the order of 10 raised to 3 kilogram per meter cube. Okay, this is Newton per meter square, this is kilogram per meter cube. Okay, so the typical sound waves, the speed of sound waves in solid is, if you substitute these order of magnitudes, you get 2 to 5 kilometer per second. Okay, it's a huge speed, 2 to 5 kilometer per second. The reason is that the Young's modulus of the solids is very high, and hence the speed of sound waves or elastic waves or compressional waves in solids can be quite high. For example, if you consider the longitudinal waves produced by earthquake in granite, it's of the order of 5 kilometer per second. So these are very fast waves. They can cover half the circumference of the earth in 1 hour. Okay, that is why a significantly large earthquake happening at a long distance away can be felt at other parts of the planet. Okay, so these waves can be very fast. Now consider sound waves in a liquid. Okay, sound waves in a liquid column. Now here the expression for the wave speed is bulk modulus ratio of the square root of bulk modulus by density. Now bulk modulus of liquids, this is bulk modulus. Bulk modulus of liquids is of the order of 10 raised to 9 Newton per meter square, and density of the liquids, this is density. Density of the liquids is of the order of 10 raised to 3 kilogram per meter cube. Okay. So liquids are more compressible compared to solids, even though there is not much reduction in the density of the liquid compared to solid, 10 of the order of 10 raised to 3. So since they are more compressible, the speed of sound waves in a liquid is somewhat less. The typical speed is of the order of 1 kilometer per second. 1 kilometer per second. In solids it can be 2 to 5 kilometer per second. Then let us consider sound waves in air. In a gas column, for example. So sound waves in a gas column. Here the expression for the wave speed is gamma times pressure divided by rho. Okay, gamma is, as you know, it's a ratio of the specific heat capacity C at constant pressure to that of constant volume, Cp by Cv. The value of gamma ranges from between 1 and 5 by 3 for different types of gases. 1 to 5 by 3. And P is the pressure of the gas. P is the pressure of the gas. And rho is the density of the gas. Okay, let us do the calculation for air. Air contains mainly diatomic gases, so gamma is 1.4, and air pressure is of the order of approximately 1 atmosphere. Sorry, the density of air. Let us take. Okay, let us consider this as density. Density of air is approximately 1.2 kilogram per meter cube, and take the pressure as 1 atmosphere. 1 atmosphere is approximately 10 raised to 5 Pascal. Okay, so if you substitute these values, gamma 1.4, density approximately 1.2 kilogram per meter cube, and pressure as 1 atmosphere or 10 raised to 5 Pascal, then the speed of sound in air is at 1 atmosphere pressure is approximately 340 meter per second. Okay, 340 meter per second. So we can rewrite this expression, the sound waves in a gas column, in terms of temperature also. Let us do this. Let us assume that our gas is an ideal gas. For an ideal gas, we can write the ideal gas equation connecting the various parameters. PV equals pressure into volume equals nRT, where n is the number of moles. Now this number of moles you can rewrite as total mass divided by molecular mass. Total m, small m is the total mass, capital M is the molecular mass. You can write like that. Okay. Now if I rewrite this in terms of density, if I take velocity from the left side to the right side, this small m divided by volume, mass by volume, total mass by volume is the density. So I can write the right side as pressure is equal to density RT divided by mass. Now in the expression for wave speed, we have pressure divided by density, right? So what is pressure by density from this expression? Pressure by density equals RT divided by M. So this means the wave speed we can write as square root of gamma, see here, instead of gamma P by rho, let me substitute RT divided by M. Okay, so this also is expression of speed of sound in a we can use either this formula, okay, or this formula. So what is interesting about the second formula is that now we can see that it is independent of both pressure and density. See here, it depends on pressure and density, okay, but it depends on, carefully when you see, it depends on the ratio of pressure and density. When one varies, the other also varies, such that from this formula it is clear that it is independent of pressure and density. So this formula shows that one speed is independent of, speed of sound in an air column or a gas column is independent of pressure and density, okay. Secondly, we can see that speed is directly proportional to square root of temperature. So if absolute temperature increases, speed can increase, okay, and speed is inversely proportional to the molecular mass. So the heavier the gas, if the molecular mass is higher, then the speed will be less. Gamma and R are two constants. So these are the various factors on which the speed of sound in a gas column depends. It is independent of pressure and density. Okay, even though pressure and density are there here, the ratio will always be. It depends on the ratio. It is independent of each variable separately. Okay. So it depends on temperature, it depends on square root of temperature, directly proportional to square root of the temperature, and it is inversely proportional to the molecular mass. Then another formula we can use for speed is from kinetic theory of gases, there is an expression for pressure of a gas. Okay, pressure of a gas from kinetic theory we can write as 1 by 3 Nm Vrms square, where Vrms is root mean square speed. Okay, N is the number density, that is the number of particles per unit volume, and M is the mass of one particle or one molecule. So there is this type of a formula for pressure. Then yeah, we can rewrite this as 1 by 3. Number density is total number of particles divided by total volume, right? So V square Rms. Again, in this formula, N is total number of particles and M is mass of one particle. So N into M is total mass. Total mass by total volume is density. So this formula you can also write as rho times Vrms square. So again, pressure by density you can write as 1 by 3 Vrms square. Okay. Remember that the original expression contains pressure by density. So speed of sound in a gas column we can write like this. V is equal to square root of gamma times P by rho. P by rho is this Vrms square divided by 3. Okay. So what you see is that Vrms square you can take outside the square root. So this is square root of gamma by 3, which is a constant, into Vrms, right? So the speed of sound in a gas column is of the order of root mean square speed of gas molecules, we can say, or of the order of the mean speed, average speed of gas molecules. Root mean square speed is very close to the average speed, and this is justifiable because in a gas column the propagation of a wave is possible. It's a longitudinal wave, right? So it is propagating by compressions and rarefaction. So propagation of a wave is possible by the physical motion of the particles of the medium. So it is natural that this wave speed is of the order of the RMS speed of particles of the medium, and this is of the order of a few hundred meter per second, a few hundred meter per second. That is the typical root mean square speed or average speed of gas molecules. So that will be the order of speed of sound waves in a gas column, and we have seen that in the case of sound waves in air at 1 atmosphere pressure, the speed is of the order of it's approximately 340 meter per second. So in general, the wave speed wave speeds of sound waves in a gas column is of the order of a few hundred meter per second. So we have seen the wave speeds in different media. For transverse waves on a stretched string, the formula is like this: square root of T by mu. In the case of longitudinal waves or elastic waves or compressional waves or sound waves in a solid, the formula is this. It depends upon Young's modulus and the density, inversely proportional to the density, and it is of the order of 2 to 5 km per second, which is a very high speed. In a liquid column, the speed is somewhat less. The formula is square root of K by rho, where K is the bulk modulus. Speed is of the order of 1 km per second. In a gas column, the speed is again less, of the order of a few hundred meter per second. Okay. And in a gas column, you can rewrite the formula in different ways. Velocity is square root of gamma P by rho, where P is pressure, rho is the density, and you can write like this also, square root of gamma RT by M. So this shows that velocity is independent of pressure and density. It depends on square root of temperature, inversely proportional to square root of molecular mass. So if there are heavier elements present, speed will be less. Okay, and it can be you can show that speed is square root of gamma by 3 times Vrms. So speed is of the order of RMS speed of gas molecules, which is a few hundred meter per second.